Hi everyone! We are going to learn about how to do limits algebraically. I'm going to run you through some problems, some easy, some hard, and hopefully it will help you carry on with these kinds of problems. So let's go ahead and get started. Problem 1. We're going to find the limit as x approaches -3 of the quotient 2 over x plus 2. The first thing that you guys want to check when you're doing limits by hand is take a look and see if the denominator is 0 or any other weird things are happening. If we take a look at the denominator, it happens to be x plus 2. If I plug in -3 into the x, ask yourself if the denominator becomes 0. In this case, the answer to that question is no, so I don't have to do any special techniques here. I can go ahead and do direct substitution. And all direct substitution means I'm going to plug in the number that I'm approaching into x, all of the x's. So if we do this process, it's going to look like this. I'm simply going to do 2 over -3, that was the x, plus 2, which then becomes 2 over -1, which is equal to -2, and then you're done. So fairly simple. So just make sure that the denominator is not 0, and this process is pretty easy. Just make sure that you follow all your PEMDAS rules. Okay, so what if you're given two different functions and you're asked to do different things with them? For instance, here I have two functions, one being f of x, which is 5 minus x, the second being g of x, which is equal to x cubed. And the question is, what is the limit as x approaches 1 of g of f of x? This is called a composition of functions. You have seen this before if you've made it to calculus, whether you wanted to remember it or not. What you want to do first is always work from the inside and work your way outwards. So the first thing I see in here is this f of x. Now, if I pay attention to the notation of functions, I want to do f of what we are approaching first. So f of x, I replace this x with what I'm approaching. It's no different than the problem before here. So f of 1. How do I determine what f of 1 is? Well, it's pretty simple. You take your f function, which is 5 minus x, and wherever I see an x, I'm going to replace it with a 1. So 5 minus 1, 4. So the first part of this problem is done. The second part is taking it all the way out to the outside, which is going to be our g function. Now, this entire piece, this f of x part, has now been equaled to just a 4. So if I were to rewrite this entire part and replace f of x with 4, it's going to look like this, g of 4. So that 4 used to be the f of x. Now to find g of 4, I find my g function, which is x cubed, and instead of writing an x, I'm going to plug in a 4. And I'm sure we all know what 4 cubed is by heart, which is 64. And that's what your answer is. If there's no weird special cases of any kind, you can always assume that you are doing direct substitution, which is how I know I can do this. So the limit part isn't necessarily super important here, as it is that you are not dealing with any kind of weird rational function, logarithmic function, anything like that. So that's the second kind of problem that we're going to see. And of course, our favorite limit of trigonometric functions. You just really need to make sure that you know your trig, ratios, facts, etc., really, really well. If you don't, it's going to create really bad problems down the line. So the earlier on that you learn these, the better off you're going to be. So first of all, I take a look at this problem. I don't see rational functions, which is really your main biggest concern. So this is direct substitution. So I'm going to do tangent of whatever I'm approaching, which happens to be pi. And we all know that the tangent of pi is equal to 0. So that was pretty easy. Okay, so what if you get a problem where there is a rational function, a fraction, and the denominator is 0? Notice here that if we were in fact to replace this x right here with 5, okay, I would have 25 minus 25, which is 0. So we run into a problem. There's a couple ways of getting around that. One of them is factoring, which is exactly what we're going to do here, because I can see that x squared minus 25 is a difference of perfect squares, which means I can rewrite it like so. The numerator stays the same, doesn't need to be factored, but this breaks down into two sets of parentheses. I'm going to take the square root of the first term, which is x, that goes in the first position of each of these binomials. One of them gets a plus, one of them gets a minus. It does not matter which one gets which when you're doing difference of squares. Then you take the square root of the second term, which would be 5. Hopefully, what this does is cancel something out, which, of course, it does. So the x minus 5s are gone. Now that doesn't mean that there's nothing in the numerator anymore. There is always going to be an understood 1 to be up there. So this doesn't just come out to be x plus 5 and that's it, just call it a day. It's 1 over x plus 5, so please be really careful about that. Alright, so let's carry on with this problem. So I now have 1 over x plus 5. So something canceled out. I'm going to try my direct substitution again. So let's take a look and see what happens if I plug in a 5 here, because that's what I'm approaching. Is 5 plus 5 0? No, it's not. So this should produce the answer for me. So I'm going to go ahead and replace x with 5, and that should yield my answer, which is 1/10. Alright, so there's one other special case like this. Let's take a look. Okay, so here's the second most common special case you're going to see. Once again, this is a rational function. See what you're approaching, plug it into the denominator. If it becomes 0, we've got a problem, which in this case we do. Now notice that there's nothing to really factor here. There's no x squared terms or x cubed terms or anything like that that we could potentially factor. So what we're going to do instead is multiply by the conjugate. And it is a tricky process, so you want to be really careful with this, and if you are weak on multiplying your radicals, you might want to practice that a little bit. So the way to do this is to simply bring down the problem without the limit. We'll get to the limit part later. So just like this, and then what we're going to do is simply multiply this by the conjugate. So whatever radical you're trying to get rid of, okay, in this case it's going to be the square root of x plus 5. You only do this multiplication by the conjugate if there's radicals. What you need to do is take the first term, which is the square root of x plus 5, okay, and then the second thing that you're going to do is you're going to take the sign that it has. In this case it started off as subtraction, and you're going to change it. That's all. And then you carry down the second term, which is a 3. That's all a conjugate is. It's the same two terms, just with a different sign between them. So what we're going to do is we're going to do the same exact thing to the denominator, because if we do anything different, we are going to change the problem, which we don't want to do. Notice that this whole piece right here, when something is divided by itself, it is just 1. So we're not changing anything, we're just going to change the way that it looks. Alright, now comes the really tricky part. This is multiplication of binomials. In other words, you get to use your foiling skills. Oh joy. So the first thing that we are going to do, I will try to color code this the best that I can. We are going to do the first terms of each binomial. Anytime you multiply a radical together, you are just left with the radicand, which is what's underneath the radical. In this case, it is x plus 5. Okay? Next is the outer two terms. So that's going to be the square root of x plus 5 and 3. So all that's going to do is, let's see, that's a positive times a positive, so I'm going to get plus here. The 3 is the constant, so I'm going to put them on the outside of the radical. Just keep everything nice and neat. The second thing that we're going to do is the inners, which would be negative 3 and the square root of x plus 5. Negative times a positive is negative 3 x plus 5, like so. And last but not least, the last two terms, so negative 3 and positive 3. That product is negative 9. All right, that's just the numerator. Now I'm going to take a look at the denominator. The easiest way to take care of the denominator at the very beginning of this is to just simply leave it as they are. Chances are something is going to cancel. So if we multiply this out, it's not going to be clear as to what is going to cancel, okay? It may or may not, but you're going to hope that it does. Now, the process that we did here, this multiplication by the conjugate, the reason why it's really useful is to simply look at the numerator's terms, and these outer and inner parts will always cancel each other out. That's the beauty of multiplication by the conjugate. So these are gone. Positive 3 root x plus 5 minus 3 square root of x plus 5 is 0. They're gone. So now what I want to look at is what am I left with in the numerator? I have just one x term, so that's going to stay. And then I have a positive 5 and a negative 9. Well, those are both constants, so I can combine them together. So what is 5 minus 9? It's minus 4. Okay? Take a look at what we have in the numerator right now compared to what's in the denominator. Does something cancel? It does. These will cancel each other out. So what I'm left with, remember that there's a 1 left up here. Okay? It will always be there no matter what. What I'm left with now in my fraction is 1 over, and then whatever did not cancel in the denominator. So now that something canceled, we want to see if our direct substitution is going to work. If I plug in 4 to this x, will it become 0? No, it will not. So we can go ahead and do our direct substitution. So 1 over the square root of 4 plus 5 plus 3. 4 plus 5 is 9. The square root of 9 is 3. And therefore that makes my answer 1/6. So definitely a little bit trickier. So those are your processes for doing this algebraically, and that's going to conclude this tutorial.